I've been involved in developing a lot of image processing applications recently, particularly based around the Zynq and the Zynq MP-SoC UltraScale, so I thought I'd put together some tips that we could look at. So really what we want to create is something like the system you can see there, which has a FLIR lepton connected to a 10-inch touch display. And it's a really simple one based around the Mini Z. And it's a very, very simple hardware platform that allows us to capture the image, so it configures the imager, captures the image that comes out, and then puts it out to display. What we can do, of course, with that, once we've got this basic platform, is we can use the tools such as SDSoC or Revision, which people have talked about today, to actually add in higher levels of application and function should we so desire. So these are a quick list of the 10 that we're going to look at, that I'm going to present. But actually there's a level 0 one, which is actually the most important tip of all. And that's really, without actually having a plan or a method of how we get from the beginning to the end and through the development, it doesn't really matter what other tips I give you about how to do in Vivado. I say this because actually I work a lot with a lot of companies, and a lot of times you turn up, the number one failing is they have no plan and they have no thought through how to go from the beginning to the end. So it's a good idea to have a clear and unambiguous set of requirements, and to have a design architecture from day one that everybody is aware that they can go through and create. And the final point is, hardware is always good to have. You can never have enough hardware in the system, because what happens if things break or you have unexpected developments or customer deliveries. So my first point is that we need to design in flexibility from day one. And this has really been a point that the previous two speakers have made about creating a platform that's adaptable and reusable and flexible. And when it comes to creating embedded vision systems for this, we tend to have a split between what goes in the processor system and what goes in the programmable logic. And a lot of it we can configure over techniques such as AXI Lite, which will allow us to configure the image processing chain that we create within the programmable logic. This allows us, obviously, it gives us a faster time to be able to respin and change the applications as we come through. So one of the other key things that we want to do as well is to be able to adapt to video modes as video modes change as they come in, or as we have a different display on the output. So there's a few areas that we can do to do this. The first one, obviously, is to think about it a little bit. But to be able to detect the video modes, there's a really useful block in the Vivado library called the video timing controller. The video timing controller enables you to either detect video timing that's coming in terms of a parallel video, so it takes the H-Sync, the V-Sync, and the parallel data, and it will give you a reported video timing mode that is coming in. It's also capable of doing video timing generation for the output, which we'll look at in a little while. But this allows us to actually be able to detect the video that's coming in, and to then actually actively configure the rest of our image processing chain to be able to take into account that video mode that's coming in. Obviously, to be able to adapt to this, we need to be able to adapt to the pixel clocks that come in, because each video standard has a different pixel clock, and we need to then be able to adapt to our image processing chain, because the image processing chain needs to adapt as well with that pixel clock. Ideally, to minimise the buffering that we need within our image processing chain and keep our latency as low as possible, we need to have an image processing chain clock that is higher and faster than our pixel clock. So we can use the video timing controller in conjunction with the AXI clock wizard, which we can configure over the AXI Lite interface to do this. So I put together a little simple example that does this. There's a lot of links at the end when you get the slide pack to some reference designs that you can see all these in. But what you can see here is that you can see on my rather scruffy desk, so I should have cleaned it before, so I apologise. But you can see the Z board with an FMC HDMI card on it connected to a PINC. And what I'm using the PINC for actually is the PINC is acting as a HDMI source, and that's actually generating different HDMI resolutions. It's going into the FMT card on the Z board, and the Z board's using the video timing controller to just actually detect the modes that are coming in and actively reporting those, and then we can configure the processing chain accordingly. As I mentioned, once we understand what the input timing is, we need to be able to then reconfigure the output. So we can use the video timing controller as well in an output generation format to actually generate the format. A big tip for this actually is that it's very possible that it can take its timing configuration when it's generating from either the AXI input, which is written by the processor side, or it can do it from the detector side of it. There's a series of registers that tell it where to pick this timing information up from. If you use the wrong if you don't correctly set the source correctly, then you'll spend a little bit of time scratching your head, going, well, I've asked it to give out this timing, but it's actually giving out something completely different. And then when you work it out, you kick yourself a little bit about it. So this is a very important one actually, the test pattern. I've got a couple of test patterns in here. And this actually relates not to something that we would put in our Vivado design, but actually that we would select when we were looking for an imager or a camera to use. And that is the ability to select one that outputs not only the video that you're going to be using and processing, but actually can output some sort of a test pattern. Why this is important is it's very difficult to actually debug if you have some issues. It's very difficult to actually debug live video because the scene is constantly changing. You don't know what it is. Whereas if you're looking for a repeatable pattern, it makes it much easier to actually come and work out where the issues within this are. So just skipping ahead a slide or so. So this is an example that I recently faced, which was a MIPI camera test pattern that we were looking at. So this is what I first received when I turned on the image processing chain. The majority of this block, I should say, actually was using standard IPI interfacing blocks, so VDMA and AXI streaming blocks, but we had a custom MIPI interface block. And this is the first image that we received. Now this should have been putting out a test pattern that just gradually incremented the pixel values. So it was quite difficult to sort of look at. This is actually what we achieved in the end, and what we were looking for to achieve, which is just a simple repetitive pattern that repeats. So having this test pattern ability within the imager and within the camera output in it really saved us a lot of time when we were actually trying to look through this and actually try and work out exactly where the error is. And the next point I'm going to make actually is how we went away and found this. But I thought it was sufficiently important to mention. This is what it looks like actually if you just ask it to send out through the raw video. So it's much more difficult to actually try when you try and use this in terms of put your ILAs in there and you start looking at things and doing memory dumps over your PS. It's much more difficult to actually determine what's going off here than it is to determine what's going off with a repeatable test pattern. Which brings us on to my third point really, which is to use the Logic Debugging resources that are available to us. So obviously we have ILAs, they're quite key. We put them in a lot of places in our designs. And I'm quite a big key fan of when we do this within an image processing chain, putting one at the very beginning so as I can see that I'm capturing my data properly, and putting at least one at the very end in my first build to make sure that I'm actually sending the data out, and connecting a few onto places like the VDMA status pins. Obviously, we've got there's some other areas that we can use. We can use the VIO to toggle resets and such like if necessary. Or if we're using a Zynq, then it's actually just as easy just to connect to GPIO or provide a little bit of software to do it. Because obviously we're in the hardware track, not everybody might be familiar and happy with writing C to actually drive the Zynq. So there's also the AXI to JTAG bridge, which allows us to write a really simple tickle script and control AXI devices over the JTAG link, which can be quite beneficial if you're waiting for your software to be developed. So as I mentioned previously at the example when we had the test pattern and it wasn't quite going right, these are a couple of examples of where we used the ILA to actually find that. So the format gave out a very simple frame valid signal. So the frame valid signal was just a single bit. It would go high when the frame was valid and low when the frame wasn't. It had a line valid signal, so the line valid would go high when the line was valid and low in the blanking period, and then it would have active pixels. In a correct application, you should see that the pixels are changing with the test pattern. The pixels are changing for the entire duration of the line valid signal. So if I have pointer. So what you can see here is the frame valid is high, you have the line valid high here, and you have the pixel valid here. So the pixel should be changing all the way through to about this point here, but it's not. So then you start zooming in, and you can zoom in and you can look, and you can see actually that the pixel values aren't coming through because they're not giving you the values that you expect it, because you've got a test pattern, the test pattern's coming through, and you know that it should be an incremental count. You can see then by looking at your ILA by your ILA, but actually it's not always changing on every clock. It's, for some reason, there's a stall in there, and your buffering's not working properly. So this ILA really allowed us to actually go through and actually put in the corrections to get that test pattern up and running once you actually look at the ILA. The other one I mentioned, actually, I'm not too familiar with how many people use the JXI, the JTAG to AXI interconnect, but it's something that you can put in there quite easily, and it allows us to control the AXI peripherals over this. So this is quite useful because a lot of images actually use SPI or I2C to actually configure them, and you don't necessarily want to always write a huge amount of software to actually sit there and write it, but you want to send register values down to change, maybe to put the test pattern mode on, or to change the vertical height or size of the camera that's coming out. So you can actually just write a simple tickle script with a few lines in your Vivado hardware manager, and actually then just send that down and configure the devices. So it works quite well to actually get it up and running. So that's a couple of my tips there for debugging. Now there's a different one about test patterns actually, where using an internal test pattern generator is also quite useful. Now it's different to the camera or the imager, because sometimes again you're developing your image processing system in advance of the images actually being available, so you want to prove out the majority of your image processing pipeline. And your image processing pipeline will consist of an input such as a parallel to AXI stream interface, your color filter arrays, gamma correction, any HLS cores that you may want to drop in there, and then your VDMA to actually write into the frame buffer. Once it's in the frame buffer, you may want to do some processing at a higher level using SDSOC or revision. And then you can obviously take it out of your frame buffer as well and put it out over your put it out to display. Of course, once it's in the frame buffer, if you wanted to, you could send it out over Gigabit Ethernet or something using the DMA engines in the processor. So what we can do is we can use the IP core the test pattern generator IP core that comes with the Vivado IP integrator to actually help us prove all that in advance of getting the sensor. And it allows us to do sort of, I call it incremental verification, really, in that it allows you to incrementally build the capability and verify it in small steps that you know are easily manageable and easily testable. Because a lot of this, when you're doing image processing systems, you end up verifying on the actual hardware itself and not so much in simulation. So this is a simple example in Vivado showing where we can insert the test pattern generator. So we have the Zynq UltraScale core here. We have the test pattern generator, which is configured over AXI Lite, and then we have a really simple VDMA core that converts the AXI streaming into the memory mapped format. Now, just a little quick tip for anybody that's working with these. I don't think I've mentioned it in the slides, but as we're working with AXI streaming within the image processing system, we use the T user and the T last frames to indicate the start of frame and the end of a line. So you can use those actually to work out where you are in the image process if you happen to look at it on a AXI, if you had a ILA core in or something like that. So this is another one that that previous speakers have touched on as well, actually, which is use standard interfaces or convert to them as soon as possible, really. In the entire, if you look at the IP integrator library, it's literally full of cores that are very useful to us to do this, and they all use the AXI streaming interface or they all use an AXI memory map interface. So what we need to do is we need to convert to that as fast as possible. And there are ways that we can do this. The simplest way, a lot of times you get parallel video coming in. It comes in as HSync, VSync, and the blanks, and then the pixel data. Other times you get it in terms of, if you're using a camera link type interface, you get it as terms of what I was just previously describing: a frame valid, a line valid, and pixel data. But there is an IP core that allows you to convert from parallel to AXI streaming, and you can do this very simply, which is shown on the next slide, which takes you through. And you don't actually have to have the VGA. If you look at it, you may think, well, I have to have the proper VGA timing to get the conversion. Actually, you don't. What it's looking for is rising edges on the relevant pulses. So regardless of whether you've got a fully compliant VGA input or you've got something that uses frame sync and line syncs, it's very easy to actually manipulate with a little bit of combinatorial logic to actually get this to work. So what you can see here is you can see simple pulses on the V-syncs and H-syncs, and then pixel data coming through, and then the corresponding AXI data being generated on the bottom. So you can see the T-valid, the T-ready, and the T-user and the T-last signals, which indicate where they are in the frame sync, whether it's the start of a frame or the end of a line. One very interesting thing, actually, because we have a few minutes, is that actually it's possible to pack multiple pixels in per clock as well. So you can have 4 or 8 pixels being processed per clock, which gives you a trade-off between latency and resource utilization. So I've mentioned this a few times as I've been talking, but VDMA memory really gives us the ability to have a nice break between the front end of the video processing channel and the back end of the video processing channel. So if we're going to do any frame rate conversions or output rate conversions, then we can use VDMA to do this. The real simple way that this is structured is we have a supervising processor. Now this can be a Zynq, an UltraScale Plus, or a microblaze. You can use this to configure your VDMA engine. Essentially all you're doing is defining a few frame buffers within the processor memory, and then starting the transfer. It requires you to write a little bit of software to actually get it up and running, but it's no more than sort of 10-20 lines with all the APIs that are provided. Obviously it stores the data in DDR, and then it pulls the DDR out, and then pulls the frame stores out from there. What's very interesting with this is how it stores data, and I've spent many hours actually looking at this and pulling my head out a few times. So it stores it in memory as it runs through. It packs the pixels in. So generally you're working with a 24-bit pixel or a 16-bit pixel, and you will have a number of lines. So you'll define your 1,000 lines or your 640 lines. But what it really needs to know is it needs to know the horizontal size of the image. The lines are quite easy to work out, but the horizontal size is slightly different. And this is what catches a lot of problems, and a lot of people fall over on this when they set the VDMA up, is that they define the horizontal size in pixels. But actually you have to define the horizontal size in the number of bytes. So if it's 3 bytes per pixel, you have to take the number of pixels and multiply it by 3, or if you're using a YUV422, then it's 2 bytes per pixels. And that allows the VDMA to write in a line of memory there. What's also very important is that you get the stride correct. So the stride is the difference in memory between where the lines are located. So the stride needs to be at least the number of pixels times the number of bytes per pixel, such that you run continuous lines, and that will pack in your image into memory very efficiently. But sometimes when you're verifying it, you don't always want to pack that image in very efficiently. Sometimes it's actually a good idea to leave a gap in between to make the stride longer than the lines, such that there's a gap of dead space in between there. And you can use that to verify that you're getting the correct number of pixels on a line that you expect. And so if you're seeing tearing or funny effects like I was explaining in my first test pattern generator image, if you're seeing funny effects, you can actually see that you're getting the correct number that you want in the memory. So it's also very useful when you're looking at the memory to be able to use the right one. So this is an SDK dump that you can see here of a frame buffer. Very simple. It's just putting out a tartan test bar pattern. As I mentioned, it's actually packed together. So it packs the 2 pixels. So it takes 3 bytes from one pixel, then another byte from another pixel to form the 4 bytes that are needed. Which, when you look at it on the left-hand side, is actually quite complicated, because then you're trying to work out and deduce what you actually want. Where does one pixel start, one pixel end? You can spend quite a lot of time doing that. Actually, if you just reformat that to be into one byte and display 1 byte, you can actually see the pixels and the pixel values are incrementing and coming through a lot easier and into a way that's a lot more readable and manageable. So staying on the memory in VDMA format, there's a couple of examples where you may want to verify the image. And you don't always want to just look at the image on a screen. If you're doing a scientific or an industrial application, you might want to actually grab the image and actually do some analysis on that and look at how much noise your system's adding into that image. So there's a few ways you can do this, and this uses SDK. So you can actually extract the image using SDK and a memory dump to and then reconstitute it as a bitmap that you can then analyze. Or you can take the data out directly and use it and pull it into something like MATLAB or Octave. The best way to do this is the example I'm going to present on the next slide, actually, which is to add a few lines into your SDK application that will allow you to write out a bitmap. So if you're working with a RGB image and you've got an RGB image stored in your frame buffer, you can write a little header. Which is shown there with a little bitmap header, and then you can just memory dump it out into a terminal. And there's a link to it at the back end of the slides, but there's a little application there that I've written in Tickle which will actually grab that and actually convert it into a bitmap that you can then run and push through. There's another way to do this, which is actually you can ask the memory dump in SDK to actually just output the raw memory to a Tickle file, and that you can then process it. It really depends on what you're looking for and what color space you're working within. If you're working with a black and white image where you've only got sort of 12 or 24 bits, then it's really much easier to get an image out of the memory. But it's a good thing to be able to do, because it allows you to verify that image. So one of the other things, actually, I did a food application for a food imaging application a while ago for somebody, and they wanted to synchronize the output, the frame coming out to an external synchronization pulse. And when I looked at this, looks quite simple, really. I can use the video timing controller that can take an external timing sync, and it will resynchronize it all. It can, but it's not quite as straightforward as it looks, which is why I put this slide in here. The problem with the timing controller in the generate mode, when it's generating the timing, is if it receives a frame signal, once it's received the start, it will, at the end of the timing, it will then free run and regenerate its own, which will lose sync with your external pulse. So what you need to do is you need to control the frame sync. You need to control not only the frame sync going in, but also the generation clock enable that's on that block. And how you do this is obviously use your external frame trigger to trigger this, which enables the clock generator and asserts the frame sync in. But you also need to configure the video timing generator to issue a frame sync output pulse as the very last thing it does at the end of its timing sequence, because then this allows you to disable the clock generator and wait until your next input comes, preventing it from continuing to free run. Which is what this looks like on this slide here, where you can see the frame syncs are coming in, the H syncs are generated, and you can see right down the very line at the bottom, you can see the output frame sync being generated, which turns it all off. So a few people have touched on this morning already, but leverage HLS. So really, our jobs as engineers is to allow people to deliver on time, on quality, on cost. And we don't do that by recreating everything from scratch. We do that by using our value-added activities to create algorithms and such like. And it's possible to do this with HLS. I've used it for a few applications, and it's very good. Obviously, we can use SDSOC as well if we want to lift ourselves again slightly above that higher level of abstraction. But just to give you an example of what it's like with using HLS, I took the standard Lena image. and I created two examples, one using HLS to do a simple blur like you would do before you do other image processing applications, and then I did the OpenCV version and the HLS version. Ran this through Vivado HLS, grabbed the two outputs, and then did a difference on the two, and I actually couldn't see a difference in between the two. What this does is it gives you a core, as many people have shown this morning, actually it gives you a nice core there that you can run through and just drop in your image processing chain. So it uses the standard AXI in and AXI out streaming formats. And if you wanted to enable it or disable it, or if you wanted to swap the red and the green pixels as the previous speaker did, then you could put an AXI control bus in there as well, which determines whether you actually did that or not. It's all very straightforward, and if I can do it, honestly, anybody can do it. So as we're getting towards the end of it all, end of this now, really, the final one is when we work with these, the image processing chain, it's quite complex. There's a lot of logic in there, a lot of interconnects, a lot of clock domain crossing in a few places. As I mentioned, it tends to be very, very much that you're testing on the hardware a lot of the time, and that you're doing a lot of respins, and it can take time to respin each design each time you do it. So make sure you use not only the out of order compilation, which is the standard by default anyway, and is very useful, but also you can also use the incremental compilation. I'm a big fan of using the design checkpoint and the rooted design checkpoint to make sure that my runs are minimized. It doesn't always, if you've made a big change, obviously then it's going to take a little bit longer because it can't use it as a template. But 9 times out of 10, you've not made a huge change. You've made a fairly minor change, and you want to minimize that. So you can use the design checkpoint to do that. And I recently used it. I had the same food application, which was targeting a Python 1300C camera. It was taking about 6 hours to place a route. Some of it might have been my laptop, but by the end I managed to get it down significantly using sort of design checkpoints and such like. That's it. I've got about a minute to spare, which is quite good. So, incidentally, I actually write the MicroZ Chronicles each week, which tells you how to use the Zynq or the Zynq UltraScale Plus. So there's a lot of so there's about 230 of them as of this week. A lot of information there on how to use the Zynq and how to get this up and working. And when you get this slide pack, there is in the slides right down the back. There's a link to about 10 or 15 different design references that I've put in there that are available on my GitHub that show some of these techniques that we've talked about and provide a base for that. So unless there's any questions, then thank you very much.